Welcome. This is Materialize, a pattern we use in luz-docs to make document reads fast. The one-line version: precompute the joins, store the answer on each document, and serve reads as a single index lookup. Then keep that stored answer true as the folder tree changes. Let's walk through why we built it and how it works. 6 steps. First, the problem: why listing or searching documents used to be slow. Second, the core idea: 4 precomputed fields on every document. Third, how those fields are computed. Fourth, the payoff for reads. Fifth, how we keep the data correct when a folder is renamed or moved. And finally, the states, gating, and retries that make the whole thing safe to run. Here's the situation before Materialize. A user asks to list or search their documents. To answer which documents may this user see, the server couldn't just read the document. It had to walk the document's folders, fetch each folder's name and its inherited security codes, climb the parent chain, then fold all of that together in code and test it against the user. Watch how the cost piles up. None of the derived data lived on the document. The document only stored references, its folder IDs, and its own codes. So for every candidate document, the server fetched each folder, walked up the tree, and recomputed the union of codes, the public flag, and the access check. For a 100-document page, that's 3 to 5 folder lookups per document, 400 or more round trips every single time the page loads. Reads are the hot path, and we were paying to rebuild a tree that almost never changes. The idea is simple: stop computing on read and compute on write instead. When a document is created, or when its folders or codes change, we calculate 4 sentinel fields and store them directly on the document. They're prefixed with an underscore to mark them as system-derived. Here they come. The 4 fields is public, a Boolean, true when the document needs no security code at all. That's the fast lane. Effective security class codes: the union of the document's own codes, plus everything inherited through its folders. Authorization becomes a single in match. Folder names, the path names in order for display. And folder security class codes, a per folder code set, so the interface can show exactly which folders this user may open. The last 2 are arrays, positionally aligned to the folder IDs. Index I always means folder I. How are those produced? Materialize compute takes 2 inputs: the document's own codes and its folders in order, each carrying its own codes and its inherited codes, and folds them into one state. Let's step through it. Seed the running union with the document's own codes. Then, for each folder in order, append its name to folder names, an empty string if the folder is missing. Union the folder's own and inherited codes, push that into the per folder array, and add it to the running union. A folder with no codes at all flags that a public folder exists. Finally, isPublic is true when the document has no own codes, and either some folder is public or there are no folders. The output is the materialized state, and because we fold in order with an ordered map, the 3 arrays stay aligned to the folder IDs. So what does this buy us on the read path? Same question: which documents may this user see? But the work has moved. Watch the before and after, side by side. Before: find candidates, fetch every folder in each path, walk the parents, then fold and filter in code. 400+ round trips per page, every load growing with depth and page size. After: 1 indexed query. Match isPublic true or effective security class codes contains one of the user's codes. The folder names and per folder codes are already on each row. Cost is paid once at write time on data that rarely changes, and reads get 10 to 100 times faster. There's a catch, of course. Those 4 fields are a denormalized copy of folder data, fast to read, but they can drift when the tree changes. 2 upstream events invalidate them. A folder is renamed, which makes the stored folder names stale, or a folder moves to a new parent, which changes the inherited codes for it and every descendant. We can't fix this inline on the request. That would bring back the slow walk. So the cascade runs asynchronously, off the request thread, and every cascade is marked, idempotent, and retryable, so it always converges. First cascade. A folder is renamed. Say reports becomes updates. Thousands of documents now hold a stale name. Here's how we fix them without blocking the user. The rename returns 200 immediately. The cascade is deferred. We fire an async event. Write a start marker, a row that says cascade in flight, so retry scans, skip it, then run one bulk update. Many. The filter matches documents that contain this folder and still hold the old name, and a server-side map swaps only that one slot in the folder names array. If every matched document was modified, we delete the marker. If not, we mark it partial. A response filter seeds a retry sweep on ordinary traffic, which picks up partial markers, rereads the current name, and reruns until it converges. At least once, with no per-document round trips. The second cascade is trickier. A folder moves to a new parent, so its inherited security codes change. And because codes flow down the subtree, every descendant is affected too. Let's see how that's handled. First, scope. The affected folders are the moved folder, plus all of its descendants. We prefetch in Java a map from each affected folder to its new code set, because Mongo can't do a lookup inside an update pipeline, so the new sets are computed first and inlined as literals. Then one update many runs 2 stages. Stage 1 rebuilds the per-folder codes array, swapping in the new set for affected slots and keeping the rest. Stage 2 refolds the effective union and recomputes is public. For bulk moves, there's a write-ahead log. We persist a marker with the affected IDs before the loop, extend it as each folder moves, delete it on success, and if we crash mid-loop, the marker survives and the sweeper reruns the cascade over the saved set. Durable intent means no lost document. Last piece. What makes this safe to actually run in production? The states, the gating, and the self-healing. 3 parts: rollout and the gate. Materialize is opt-in per tenant via an allow list. A backfill migration stamps existing documents in batches, and a completion gate uses materialized reads only once everything is stamped, falling back to the legacy path otherwise, with the complete status cached for about an hour, and the incomplete status for only about a minute, so it rechecks often during rollout. The marker state machine. Start means in flight and is skipped by scans. Partial means some documents matched but weren't modified, and only those are swept. Fully applied markers are deleted. And self-healing. Ordinary reads seed the retry, transient errors retry with backoff, and each sweep clears more markers until the cache is consistent with the tree again. So why does this design hold up? It's read optimized. The hot path is a flat indexable filter. It's order safe. The arrays stay aligned to the folder IDs. It's crash safe. Write-ahead markers mean a bulk move never silently drops a document. It's self-healing. Partial markers get swept by normal traffic. And it's safe to roll out a per-tenant allow list, plus a completion gate that keeps the legacy path until backfill is done. That's Materialize in one breath. Move the work from read time to write time. Store the answer on the document, and serve reads from a single indexed match. When the tree changes, an async, marked, retriable cascade quietly restamps what's stale. A denormalized read cache that keeps itself true, fast for users, and invisible in its upkeep. Questions?